So I have to figure out how to share the screen. I guess I never used this one.
There's a green button on the bottom.
Yeah. It doesn't show my, okay. I guess it does. No, that's a different one.
Yeah, it was.
Yeah, but I need Adobe. Here it is. Okay, this one. So do you see it?
Yes.
Just maybe go full screen. Yeah, perfect.
Yeah. So it's not completely full screen because I want to make some notes on the site. But let's see. Yeah, I can move this window. Okay. So you see the whole screen, right?
Yes.
That's good. So yeah, I didn't know how to call this talk, but I ended up with this awesome name, like hardening and fault-tolerant distributed algorithms with model checking. It's not really about complete verification, but it's about improving algorithms by doing verification or model checking. So yeah, if you are in academia, you have this awesome picture, right? Usually you'll hear in the first lecture this awesome picture how you develop distributed algorithms, right? You have an algorithmic idea, and then you specify it in a domain-specific language. You verify it because there are good verification tools. Then implement it and verify the implementation, or some people would say you should synthesize the implementation, right? And then you have a distributed system which is perfect and it's working, there are no bugs. And I think you all know that this unicorn is here for some reason, because it's all not true, right? So first of all, when we started doing it with Joseph like 6 years ago, we started to see all these problems immediately, right? And I guess you know all of them as well. So first of all, there is no common language, right? So how do you make a domain-specific language here? Then there is another problem. There is no language for verification. There is no common language for verification. And I think Žarko is very happy that he can write pseudocode, but we are not very happy about having pseudocode. We want to verify it. And of course, there are many computational models, and different model checkers require different computational models, right? So as a result, we actually have a lot of bugs in these systems, and it's not so easy to verify them. So actually, there are several reasons for that. First of all, usually model checking or model checking tools work on finite state spaces. But what you guys have infinite state spaces, everything is unbounded. Usually you have parameters such as number of processes, and you have faults, right? So all these things make verification complicated. And automatic tools usually stop working when you have faults or parameters, right? So the problem is real. I mean, I don't have to explain to you, I guess, but here are a couple of algorithms that actually had bugs in the past, right? I guess you all know Raft, and they had a couple of bugs that they have discovered by Murphy. So they were encoding the algorithm in Murphy and found some bugs, but some of the bugs were found just by looking at the pseudocode and the TLA specification. And what I recently learned is that actually people used TLA model checker, TLC, they used it at Apache Kafka, and they found actually several real bugs in the system, and they fixed them, hopefully, right? So this problem is actually quite real. So what I did in the last 7 years, I guess already, I was working on verification and synthesis of fault-tolerant algorithms, more verification rather than synthesis. I have one paper on this. This was done mostly at TUV in Vienna, together with Josef Eder and others. And now I'm continuing this work at INRIA. And what we recently started to do, we started this project on model checking of TLA+. So we are developing a new model checker. And what I did in the past, I was developing some methods on, more theoretical methods on parameterized verification, parameterized model checking. So this is less interesting for you, I guess. But the first two things should be interesting, right? So that's the structure of the talk today. So first I want to talk about the Byzantine Model Checker, but I guess Josef Eder already gave you some idea about the algorithms and the techniques that we have implemented there, right? So I will just quickly go over the ideas here. And then I want to continue with this Appalachian model checker that we're developing nowadays for TLA+. And somehow, when I will discuss this model checker, I will go to Tendermint, because I want to give you an example of how the Tendermint consensus algorithms can be checked. At least some parts of it can be checked with this new model checker, right? So what do you want to hear more? I mean, should I give you more details about the first one, or should I give you more details about the second and the third?
I vote for second and third.
Okay, so I'll just quickly go over the Byzantine Model Checker, and yeah. So that's what we did in the last 6 or 7 years. I don't remember how many already, right? What we have here, we have a distributed system, right? We have a system of n processes. Some of them are correct, some of them are Byzantine, right? And nobody knows how many Byzantine processes we have, how many faulty processes we have. But there is an upper bound on the number of faults, right? And typically you want to verify the system for all the parameters, all n and t and f, where t is an upper bound on the number of faults, such that n is greater than 3t, or you can have different conditions here, right? So that's what algorithm designers want us to do, right? Unfortunately, this problem is quite hard. It's called parameterized model checking, and usually it's undecidable. It's decidable for a very specific framework I'm going to talk about. But in general, if you want to check something for all parameters, it becomes easily undecidable. So you can reduce this problem to termination in Turing machines, right? The halting problem. So I'll just give you one example of an algorithm that we have in mind when we are talking about these things, right? Here is one-step Byzantine asynchronous consensus. It's not as powerful as Tendermint. It's just a preprocessing step, essentially. And what you have here, you have that every process starts with some value, 0, 1. Then that's the specification, right? You want to have agreement as usual. You want to have validity. And you want to have termination, right? And then you have this property, correctness property, that if everybody starts with a value, everybody decides on this value eventually, right? So what Bosco is doing, this is Bosco, right? It actually decides in one communication step if there are not so many faults. And his pseudocode, that's the real pseudocode from the paper. Again, it's much simpler than Tendermint, right? What has happened here is that initially everybody has an input, in our case 0, 1. Then every process, every correct process sends its vote to all processors. Then they do some waiting until they receive enough messages, sufficiently many messages, and then they make a decision. So if there are a lot of processes who actually send the same value, they can decide immediately. If there are a lot of processes who send 0, they decide on 0. If there are a lot of processes who decide on 1, who send 1, they decide on 1. Or if there are not so many processes, you do something different, right? You call the underlying consensus. For instance, Tendermint, you can try to call Tendermint here, right? And there are different cases when you call this underlying consensus with a value such that you have some number here, or you call the underlying consensus with a value that you initially had, right? So there are different paths through this graph. Or you just decide immediately and you don't call the underlying consensus. So that's one of the algorithms we can actually check with our Byzantine model checker. We cannot check pseudocode, right? And what is known from the literature is that it actually terminates fast when you have sufficiently many correct processes and no faults, or it terminates fast when you have a lot of correct processes, right? So that's Bosco. So the first thing we can do, if you want to formalize it, we can specify it in what we call parametric parameter. It's a lot of code, you don't have to read it. I just want to show you that you have to do this formalization step, right? And what we do here, we write a lot of assumptions. We introduce variables that accumulate how many messages everybody has sent around. Then we introduce variables that tell you how many messages we received. And then we introduce variables that tell you where we are, right? So we have all these variables. We write some code that tell us how many messages we can receive. There are some conditions here. And based on this number of messages and the current state, we can change our current state, right? Every process can change its current state. So it looks a bit ugly and it's a bit complicated because we actually have to make it compatible with the code that the model checker spin would use. So everybody was telling us we should use the input language of a real tool, and that's kind of a special version of the input language by spin. That's a famous model checker, right? So that looks a bit ugly, right? What we understood later is that we can use something much nicer, what we call threshold automata, right? It's just an automaton. You all know finite automata, right? What you have here is that every process resides in one of the initial locations, like, I don't know, it must be a typo. So initially I have either 0 or 1, then I send the message, right, and go into the next location. And when I send the message, I increment the shared variable here. It tells me how many messages I have in the system, how many messages sent by the correct processes I have in the system. And then based on how many messages with value 0 or 1 were sent, it takes these decisions whether we whether we decide fast here, right? Or we decide, we go into the underlying consensus, right? And then you have another copy of this automaton for value 1 here, right? So this is a threshold automata. If you manage to write the input like this, we can verify it, right? It's not Tendermint, it's much simpler in some sense, but there are several algorithms that actually can be encoded in this threshold automata. What you have here, what's important here is that you always increment the shared variable when you send a message, when you broadcast a message, and you also count how many messages you have received, right? And this is done by checking how many the values of the variables plus possible messages from the faulty processes, and then you compare it to the threshold guards. So if you have a threshold automaton like this, and there are many algorithms like this that only use threshold conditions, right? So there is a reliable broadcast, hybrid broadcast, some forms of agreement, some forms of what is called consensus, but you know it's not real consensus, right? It's some kind of preprocessing steps to consensus. So there are several algorithms like this. We can check all of them, right? Here's our Byzantine Model Checker, right? If you give me a threshold automaton encoded in some text form, right, in our input format, we can run the Byzantine Model Checker, and we managed to verify 10 parameterized algorithms that come in this form of threshold automata. So that was presented at Popple and CAV. These are really the best conferences in verification. And they also looked at our code and examples, so it works. Although some people complain the code is not perfect. Yeah, we are not doing perfect code in research, unfortunately, right? So yeah, that's the Byzantine Model Checker. And I just give you 2 slides about how it works in principle, right? I guess Joseph explained to you more things about it. So the crucial idea here is that we do bounded model checking. So in principle, if you want to find a bug, you should explore some execution here, right? And if there is a bug, you should be able to find it. But in reality, we can only explore bounded executions up to some bound. So we can encode a bounded execution in a tool, in a SAT solver or SMT solver, and explore all bounded executions up to this bound. And what we have found out is that actually for the algorithms that can be encoded as threshold automata, if there is a bug that is reachable via a long execution, there should be a shorter execution that reaches the same buggy state, right? So it's not as easy as I say, the result is like this, but the proof technique is quite complex, how you prove it, right? And what's more interesting is that it works for reachability, but it also works for safety and liveness properties. So if you have a very long lasso execution, right? If you have an infinite execution that has this shape, right? Then you should have a short execution that has the lasso shape and it's still within the bounds, right? So the length of the prefix and the loop is still within this bound. So this allows us to verify, actually completely verify the algorithms that are encoded as threshold automata. And this works in the parameterized setting. So we can do, we actually check whether these algorithms work for all combinations of parameters, right? So what we realized later when we ran the experiments, that if you just explore all the executions in the execution space, that's very inefficient. What you can actually do, you can look at the structure of the transitions you have, like and the thresholds, right? And then you can see that many of these transitions, they can be swapped, right? So we use something similar to what is called Lipton's reduction. We reorder some of the transitions, and there are some conditions when you can do that, right? So when you reorder these transitions, you realize that you actually can merge together many of these transitions. That is what is called acceleration, right? So we do acceleration, and by doing this swapping and acceleration, we actually we can take a very long execution and turn it into a shorter one. And we can tell you how long this execution should be, the short execution, right? So that's the basic principle of what is implemented in the current version of BIMC, right? And I guess Joseph told you more about how it works, right? So we were very happy actually that it works for liveness and safety, and in the end we could check 10 algorithms. So here's our verification algorithm from a more engineering perspective, right? What you have here, you have a threshold automaton in the input, and our tool actually constructs a set of schemas. So schemas are something like patterns that tell you what kind of execution scenarios you should explore so that you find the bug. And if you explore all of these patterns and you don't find the bug, you know there is no bug in the system. So what our tool does, it takes all of these executions. They can actually have the shape of a lasso, right? So they can describe the infinite executions. And then it feeds every of these executions to the SMT solver, Microsoft Z3. So if this solver tells us one of these patterns can produce a counter, it has a satisfiable model, it means we have a counterexample. So we can give you a real execution of the system of threshold automata that actually corresponds to a buggy behavior, right? You violate the safety property or a liveness property. So if it's a safety property, right, you have just a trace that tells you how it's violated. If it's a liveness property, you have a lasso, a bounded lasso, right, that tells you what you should do in order to never reach a good state, for instance, right?
Well, how do you come up with the schemas in the first place?
So first it was a long story actually, right? So first we used some abstraction techniques, and I ran some experiments in NewSMV, that's a classical model checker, right? And then what happened there is that we couldn't check the properties. NewSMV was just exploding like crazy. But I told Joseph, look, it looks like all these executions are actually quite short. So we started to look at this stuff, and we found out that there is a bound, right? So it took us about a year actually, to prove that there is a bound. We found out there is a bound in the executions. You can reorder a lot of things. But then the first proof was just talking about the long executions and short executions. Then we looked carefully at the structure of the proof and essentially figured out how you construct these patterns, right? Because essentially what happens there is that you look at the orders between the edges in the threshold automaton, right? And you say which edges you can move forward, which edges you have to move backward, right? And you also say that there must be some critical edges that you cannot move. And these critical edges actually change the global state of the system. They go over the threshold, right? You increase some shared variable, and all of a sudden, you know that the number of messages is greater than t+1, right? So there are some critical edges. Then you do a lot of sorting, and that's what we did in the original proof. We just said there is a sorting mechanism, right? But then later we realized how to do this sorting. Well, not manually, but there is an algorithm, right? So it wasn't a single step, right? It was like 2 or 3 steps how we came up with this idea. But that's actually a very powerful idea. So these reductions, they should work for a much more general class of algorithms, I believe. It's just much harder to prove that, they work for all classes of algorithms, for instance. Yeah.
But is this like analysis of the automaton itself, or it also somehow reflects the understanding of how algorithms work?
It's both. It's both, actually, right? I mean, so we looked at these algorithms, right? And so if you have a condition like the number of messages is greater than t+1 or n minus t, if I know that this is happening, right? It's most likely the case that you should also know the same thing, right? Because in the global state, the counter of the number of messages sent by correct processes is the same. You have Byzantine processes, they can add a bit of faulty messages, but otherwise it's we basically have the same information, right? And that's how we construct these patterns, right? We say that there must be a critical edge that changes this global knowledge. We don't talk about knowledge, but essentially you say you change the global state and then everybody can move, right? And what's important here that you have several edges like this, and in between you order all processes, how they move, and then you accelerate the transitions. So I think it's also understanding of how these algorithms work. It's actually a lot of understanding of how they work. But in principle, this reduction approach, it should work in many other algorithms, not only the threshold-based algorithms.
What's the difference between the model checker and the verification algorithm that allows you to reduce the automaton in the case of the verification algorithm to like a finite SAT problem, whereas you have to have this execution bound in the model checker?
Right. So if you want to reduce a parameterized algorithm to a finite state system, right, you have to apply some abstractions. Say you have to say, instead of keeping track of precise numbers, say 10 messages or 15 messages, I map these numbers to some abstract domain, say to intervals, right? Then you do this mapping and you feed it to the solver, for instance, or a finite state model checker. So if the model checker tells you there is no problem, it's all good, right? But then if the model checker tells you that there is a bug, you have to somehow refine it. You have to look at it as a user, or you need an automatic procedure that looks at it and tries to understand whether it's a real bug or just some artifact of the abstraction you applied, right? And in this case, we don't do abstraction at the level of the message counters. So they're integers, right? You feed them to the SMT solver that can solve linear inequalities, systems of linear inequalities. And if it tells you something is SAT, if it has found a model, it's a real model. There is no abstraction involved, right? So that's a major difference. Does that answer your question?
Kind of. I guess I still don't quite. So in the model checker, what I heard you just say was that the verification algorithm was concrete, whereas the model checker was abstract. But I thought it was the model checker that had to have an execution bound, whereas the verification algorithm can like prove that there are no cases when an algorithm can violate something.
Ah, I see. I see. So that's
like, be able to do with the abstraction as opposed to like concrete state spaces which are infinite. Does that make sense?
Yeah, I guess the confusion is that I'm talking about the model checker and the verification algorithm, right? So this verification algorithm is implemented in the model checker, right? So these are not two different things, right? It's just the algorithm that is implemented there, right? And so our model checker, it's not like a classical model checker, right? It doesn't just enumerate states. What it does, it computes this bound, and it constructs the schemas, and then it feeds it to the solver, to the SMT solver. And then if there is a bug, it will tell you there is a bug, it will show a counterexample, right? So I guess there is a confusion here that classically model checkers are something that take a crypto structure transition system, a finite one, and then they try to find some executions in this transition system, right? Here we have infinitely many states in principle. That's why we cannot, explore all the states. What we do here, we actually explore all the executions up to some bound. And that's what we can do here. Because we know there is a bound, we can construct a system of linear inequalities.
I see. So we're proving that we're verifying still within that execution bound.
Exactly. So we're verifying things in the execution, up to the execution bound. And there is a huge theorem, like 10 or 15 pages, that tells you that if you do this, then the algorithm is correct, right? If you haven't found a bug up to this bound. Okay, so there is some manual part of this technique that tells you that for all kinds of threshold automata, you can find the bound, and here's how you find it, and you can construct the schemas, and here's how you construct them. And once you did that, you know that the bugs should be within this limited execution space. So you have some bound on the length of the execution and some bound on the execution space. Okay?
And this is because of some like isomorphism between finite automata states, or you said it was a 15-page proof. Is it possible to?
That's a good question. I mean, we never managed to prove this statement, right? It's what many people are asking actually, whether you can prove that if there is a large system that has some execution, there must be an execution in a smaller system. And it's very hard to prove for these kind of algorithms. Right? What we managed to prove is that you actually still explore infinitely many executions of infinitely many processes. You have a system, infinitely many systems of n processes, right? But you only explore executions up to some bound. So the proof is different from standard abstraction techniques or standard model checking techniques, right? So just say that you reorder transitions and then you explore executions up to some bound.
Mm-hmm. Yeah. Is this proof general for all threshold automata?
Exactly. Yes. It's not just for 10. It's for all threshold automata. Well, there are some constraints on how they should look like, right? We have some constraints on the loops that can happen in the threshold automata. And we only allow to increment variables, for instance. The moment you decrement variables, everything becomes undecidable. But you don't decrement variables in these algorithms, right? Because you send messages. You kind of don't forget messages here, right? So you don't erase your memory. Okay. So shall we continue, or there are more questions?
Not for me, thanks.
Okay. So yeah, and then we ran actually this tool on, basically I ran it on my laptop, but then we started to verify larger and larger algorithms like Bosco. And in the end, we had to use the scientific cluster, right? So that's the last thing we did like a couple of years ago. So what we realized is that these queries they can be checked independently in different nodes of the cluster, right? You don't have to check them one by one. That's a very simple parallelization technique here, right? But the good thing is that you actually can check a lot of things in parallel. So that basically ends the part about the BMC, right? So basically you can verify and synthesize 10 or maybe 12 algorithms that have this nice shape of threshold automata. We can do it in a cluster, and we can use different formats like threshold automata and Parametric, right? So it's all good. We are very proud of this work. I'm proud of this work, and Joseph and other co-authors, right? But then we always asked whether can we add a bit more to threshold automata, right? Can we add a leader election? Can we add failure detectors? Can we add time, whatever, right? So in general, distributed algorithms have many more primitives than that, right? And I don't know whether you see it. I have to delete some things here. Okay, hand here. So do you see this notification? So it's just me. Okay, I guess you don't see them. So a couple of years ago, actually in 2016, we have started this project on a model checker for TLA Plus, right? Because TLA Plus actually allows you to explore, to specify arbitrary algorithms, essentially, right? So TLA Plus is used by industry, you know, it's introduced by Les Lampert, blah, blah, blah. So the standard phrases, right? And what we want to do, what we are doing, we are developing a symbolic model checker that doesn't enumerate states, because the current model checker actually enumerates states, and that's not very efficient, right? And maybe in some distant future, we want to do parameterized verification, but that's not the focus now, right? So it's supported by Vienna Scientific and Technology Fund, and now we have essentially the team split between Vienna and Nancy in France, right? So these guys, Stefan Meretz and his students are also working on the interactive proof system. So there is a lot of things happening here in Nancy. So why TLA, right? Well, one reason is that Les Lampert is promoting it, so he's telling how to use TLA, and that's a great language, right? And the other reason is that actually many distributed algorithms are implemented in TLA. You see here several names. There are more algorithms like this, right? And not of them can be easily checked with TLA tools, but some of them actually were checked, right? So we don't know exactly what's happened at Amazon, but from their papers, we know that they have found several bugs in their consensus protocols. And there were several bugs found in Kafka, for instance, right? So for Paxos, there is a proof in TLA proof system that it actually works for the C-node algorithm. So TLA is like this general language where you can express whatever you like, but then it's getting a bit hard to verify it, right? So what we did, that's a new thing, right? What we are doing right now, we are developing this symbolic model checker for TLA Plus. And now we have the first tool that actually works, that can check some of the algorithms. It happened to be not so easy to develop this tool. It actually works in several steps. First, it looks for assignments and symbolic transitions in the code. I will not tell you what it is, but believe me, it's not so easy, right? Then we do some type inference, because TLA Plus is untyped. And then again, we do bounded model checking. And again, we use SMT solvers. But this time, we don't have any bounds that tell you how long the execution should be, right? You can check this link at GitHub, the unstable version, because the stable one is very old. And, well, we are currently trying to check some real specifications. But I will not talk to you about the specifications that other people are doing. I just wanted to show you some power of TLA in application to Tendermint, right? I only focus on safety here. Liveness is a bit too much for one talk and several weeks. So, of course, if you want to verify something, if you want to check or find bugs, right, you have to make some assumptions. And here are the assumptions I'm making, right? So the processes have voting power of 1. I know you have different assumptions about it. the hashes are just identical to the values, right? So there is no hashing essentially. Then essentially there is no time, so there are non-deterministic timeouts, right? Whenever you schedule a timeout, it can happen anytime. And then there is a proposer that is just a function that tells you it's deterministic, right? So it tells you given a round and the height, the process ID of the proposer. And that's also important, the faults are injected right in the initial states. So whenever you start the system, the faulty messages are already there. So it works for safety, it doesn't work for liveness perhaps, but these are the assumptions for safety verification, right? So just a note about the voting power. So I think, I don't have a proof for you, but I think that if you reason about processes with voting power of 1, and you don't find any bugs here, it should be sufficient, right? Because if you have processes with a larger voting power, you can always decouple them into a series of processes that just work, you know, they copy each other's behavior, right? So I think if you check things for power of 1, that should be good. And actually, that's a bit similar to what we did with acceleration, right? Because they say several processes make the same step at the same time, right? So that is somehow related to the voting power, I believe. But yeah, that's the assumption. We only have voting power of 1. I don't know whether you can have voting power of, you know, 1/2, but I would suspect it might break liveness, right? I don't know. You know it better, I guess. So let's try to express this algorithm in CLA+. I'll just give you a bit of code, not the whole specification, right? So you have this pseudocode in the Tendermint paper. I just took it and wrote the CLA+ spec. So what we should do first, we have to introduce some constants. This is just the syntax in CLA for essentially operators or constants, right? So we introduce the number of processes, the number of faults, the actual faults, and the upper bound on the number of faults, right? In the expressions, we will always use the upper bound like this, and we will never use the actual number of faults, right? Then we restrict the number, the set of heights and the rounds because we are doing model checking. It should be bounded, right? And then we introduce the values that you can have. You can make this sets larger, which will make the problem harder, but you should somehow define the finite sets here. And there is a special value for nil, of course, right? So what we do here right away, we say that the correct processes have these IDs from this set, from 1 to n minus f. The faulty processes have these IDs from n minus f plus 1 to n. That's not really essential because you don't use IDs, right? So it's a good assumption here. Then what we should do, we should declare some variables. And here you see it's nicely, it's like one-to-one correspondence to the variables in the pseudocode, right? So in pseudocode, we just say you have these variables for the process P, and we say we have functions from the correct processes to the corresponding sets of heights, rounds, messages, or steps, right? Values, and so on and so forth, right? So it's very easy to translate variables. Then, unfortunately, there are things in pseudocode that are missing, right? So we have to introduce additional variables that keep track of how many messages were sent around. And these are just sets that map height and round to the corresponding records that look like that, right? So just a record that tells you who has sent the message, what the proposal was, the value of the valid round, and so on and so forth. And there are several variables for the timeouts because we should trigger timeouts only once, right? So we introduce these variables. And then, well, there is a bit of other things to do. We have to say what our constants are, right? So here, we don't know what the proposers are. We just say it's an arbitrary function, right? We tell the model checker that it should pick a function from heights and rounds to processes. And it can be any function, actually, right? So, for instance, you can always have an execution where the proposer is just faulty all the time. It's not fair, liveness will not work, but for safety, it's like we're on the safe side here, right? We of course could implement round robin here, and that's the power of TLA. Whatever you like to write, you can write it in short expressions. So how you specify the transition system? You just define a lot of what is called actions. These are essentially formulas, right? And each of them works over a process. So you say there is a process such that it fires an action like this, right? And essentially all of these actions are just the lines in the pseudocode that are called upon something, right? I'll just show you two actions like this because it's too much information, right? So if you have this line in pseudocode, right, 2 lines in pseudocode, we introduce an action like this, and then we add all the conditions that you have in the pseudocode. We just write them in TLA+, and there is not so much difference here. For instance, if you have step equals prevote, you write step of p equals to prevote, and you count how many messages you have sent around. It means you take this set of messages and compare its cardinality to the threshold that you have there, right? Then there is something tricky about the first time, right? What we do here is say, okay, let's introduce an event, just a record that collects all the information here, right? And if we don't have it recorded in the global state yet, we just add it in the global state, and this transition can execute as soon as it wasn't in the global state, right? And then we schedule a timeout. It's just a tuple of 3 values, the process, the height, and the round, right? So that's how all of these actions look like. So here's another action on timeout pre-commit, for instance, right? You check that you have scheduled a timeout, then you remove this timeout from the set, and you start a new round. And that's another action that encodes all of pseudocode for the start new round, right? And there are 2 cases when you have a timeout for something that is useful, and you have a timeout for something that is not useful, right? When you are in a different round, so you don't care about this timeout. It just delete it from the set of timeouts, right? So there is something about initialization here. You have to initialize all your variables. And as you see for the global variables that you have in the pseudocode, it's all easy. Just say they are functions that map something to something, like processes to values, or just mapping processes to values, or heights to other values, right? So it's all easy. It's almost like in pseudocode, but a bit more syntactic. Then we have to define something about the message system, right? And that becomes a bit more complicated. So here we say how we initialize the messages in the initial state. And that's just encoding of what you have in the pseudocode again, right? So if I'm starting the round with a height 0 and round 0, then if I'm the proposer of 0 and 0, it sends a message like this, right? And this is basically, these are the messages sent by the correct processes. But then you have the messages by the faulty processes, right? And I'll tell you in the next slide what these are. But essentially, in the initial state, you have these sets of additional messages that are injected by the faulty processes right away. And then you schedule one timeout, as you can see in the pseudocode. The rest of it is just easy and simple, right? So the faulty messages are here just all possible messages the faulty guys can send. So here I say the faulty proposals are just a set of records, just a syntax for the set of records, where the source, they originate from the faulty processes, the values come, you can send any values, right? And you can send any round information here, right? So you inject any possible messages by the faulty guys. Okay, so what can we do about it? I actually ran this specification in our tool, and I know that many people are afraid of verification tools and, model checking, and that's what, I guess Amazon guys came up with. They tell everybody that model checker is just a simulator, and in some sense it's true, right? So it's something that takes a specification. It encodes a symbolic execution, so it encodes many possible executions in a formula, and then it tries to find a bug, so it tries to solve this formula. So what I did here, I actually, yeah, something's missing here. I actually first checked the specification, and you have just 4 processes and no faults. It's a bit long, 16 hours, but you know, up to 15 steps of the algorithm, you don't violate the agreement, right? And if you add 1 fault, up to 13 steps, the agreement is not violated. It takes a bit long. Our tool is not very well optimized yet. I hope it will change in the future, but still you have some confidence that, you know, it at least works in the initial phases, right? And what's interesting here that it's still faster than, you know, just explicit enumeration of all possible schedules and states. Say TLC would fail here just because there are so many messages from the Byzantine processes, right? So if you add a bit more faults, if you have 2 faults, the model checker actually can find an execution that violates the specification. So here you need 7 steps. And if you're really like, you don't want to do anything, you just run the tool, it will find you a bug in 3.5 hours, right? So what happens here is that, so some processes decide on 1 because they have enough messages from the faulty guys and themselves, right? And then another process, it switches to the next round, and it does the same. It has a message from the faulty guys and itself, and then it decides on 0. So it's a simple counterexample here. What's interesting here is that actually if you apply the brain a bit, you can find this counterexample much faster. You can find it essentially in 4 minutes. What you do here is that you say, let's find an execution that ends up in a deciding state. Just any execution that ends up in a deciding state. And then restrict the model checker only to look at executions that have the same prefix. Not exactly the same prefix, but it's using only the same kinds of transitions, right? And then you say, okay, now find me the agreement violation. Then it takes +4 steps, and it actually finds a violation in 3 minutes. So if you know how to restrict the execution space, the model checker works much faster. And I guess this idea of, you know, helping the model checker, it's in distributed algorithms, it's everywhere. You can actually improve the verification times much better than, you know, just by running it, like by pushing the button. And the other thing that I was actually quite curious about is what is happening when you have 5 processes, 5 correct processes, 1 fault. So you actually violate these requirements that you have in the pseudocode, right? So you say n should be equal to 3t, and here it's violated because 5 is not equal to 3. 3t plus 1, sorry, 3t plus 1. So I couldn't find any bug just by running the model checker. But then, actually, again, if I apply the same idea, if I find an execution where a decision is made, I can find such an execution very, very quickly. And then I extend this execution so that the agreement is made using the same kinds of transitions. And I say, find me something where agreement is violated, right? It again didn't work well. I had to wait a lot. But then I realized that actually that I can exclude just 1 action. And this is the action. I guess you have intuition why it takes a lot of time. It's actually kind of a very strange action that, you know, breaks the solver all the time, right? So if I exclude this action and say that no decision should be made for 7 steps, then I find an execution in 1.5 hours, right? So again, if you apply a bit of thinking here, you can find interesting execution. And here's an example, right? How it works. So 1 guy proposes, then 2 guys pre-vote, 2 guys pre-commit. Then this guy decides on value 1. And there is a timeout on pre-commit. This process switches to round 1 from round 0. Then it's fires propose. And then again, these 2 guys pre-vote. because this guy also switched to round 1. They pre-commit and they decide on value 0, right? So that's what the model checker is finding. I'm just showing it in a nice format, right? So that's the case when n equals 5. And I guess if you fix your thresholds to be like this, n minus t, it should actually work. So I tried to run it with a model checker. It didn't find errors up to length 17, but I don't have a concrete proof. I guess if you improve this threshold, you can exclude some of the agreement errors here, right? So yeah, that's basically what I did in the last maybe 10 days with the TLA specs. Of course, there are a lot of other things to look at. Liveness, the specification is not good for liveness, right? I didn't look at timeouts at all. Then there is something about the fairness of coordinator I should look at. And there are other algorithms that are left, somehow left out of the paper, right? So you definitely should have something like membership change. You have this gossip algorithm that you don't specify in the paper, right? And there are some assumptions that are also not explained there, right? So I guess something can be done here. I hope some bugs can be found, right? Or if the bugs cannot be found, to get more confidence in that it's working correctly, right? And I just want to conclude with this slide. So I just want to say that there are different flavors of verification, right? When people say verification, they mean, different people mean different things. And there are somehow layers here, what you do. You can do model checking at the algorithmic level. That's what we are doing now. And somehow it doesn't require a lot of, people here, right? You need smart people from the engineering side and from the scientific side, right? And if you want to do model-based tests, and you need more engineers, I guess, because you have to look at the actual code, right? And if you want to find concurrency bugs, you need a bit more engineers again, because you're dealing with the real code, right? And then there are these more theoretical activities, like proving conformance of the implementation to the specification. I guess you need more researchers here, right, than engineers. And of course, there is this, ultimate goal of proving everything correct that requires a lot of research and less engineers, actually, right? So I just want to say that what we did in the last years is this level, model checking at the algorithmic level. But I guess we can also try to go down here. For instance, model-based testing based on the specs, the TLA specs or other specs, should be very useful, I guess, for the systems we are developing. Yeah. So, yeah, if you have any questions, I'm happy to answer, and I will be happy to find any bugs in your code or the algorithms.
I do have another question.
Yes.
Go back 2 slides to the one where you had like an example execution. Yeah.
This one. Yes.
I'm pretty confused as to how process 2 is pre-committing at time step 3.
Okay.
When only 2 pre-votes have been received.
Right. It actually receives 3 pre-votes because there is a faulty guy who sends any kinds of messages, right? So 2 pre-votes here means you actually have 3 pre-votes. One from the faulty guy, which I didn't see that because I'm blocked here a bit. So we have 1 pre-vote here, 1 pre-vote here, and 1 pre-vote from the faulty guy. And then the same has happened here. You have 1 pre-vote from here, 1 pre-vote from here, and 1 pre-vote from the faulty guy. So the faulty guy is just free to lie you whatever it likes, right?
And threshold is 2f plus 1. So
yeah, exactly.
Because what for simplification, we say in the paper that it's like n is 3f plus 1, and then we use threshold 2f plus 1.
Yes.
I think this is very, it's kind of very nice what you did here, that actually showed that if you kind of ignore the fact that n is constrained, it's not correct anymore. And then, so if you actually increase n, you are, you can then see how it doesn't work anymore.
Yeah, but you're very careful in the paper, right? You say n is equal to 3t plus 1, 3f plus 1. So, yeah, there is no bug in the paper. Let's put it this way.
Got it. Thanks.
Yeah.
So I guess so with these model checking runs, you're only using 2 rounds of
Yes.
Tendermint execution.
Yes.
So
Yes.
what is it doing for 17 hours if there's only 4 processes in 2 rounds?
That's crazy, right?
Yeah, I don't understand where all the paths are coming from.
Yeah, but think about it. You have a lot of messages from the Byzantine processes, right? You have actually a lot of different schedules here. And the model checker, it has to look at really at all possible schedules of the transitions. If you're smarter than that, right, you have to explain the model checker that there is a lot of symmetry going on, that you don't have to look, say, if process 1 made a step and then process 2 made a step, you actually can rename them and nothing will change. But the standard solvers, they don't know how to exploit this kind of symmetry.
So essentially, they like this solver. They look at the global state, and in global state, whatever moves is kind of separate execution. This is what essentially.
Yeah. So you have a completely.
All interleavings are kind of possible there, and although many of them, as you say, are just completely equivalent.
Exactly. If you look carefully at these algorithms, and that's what we did with threshold automata, right? You understand how you refine the execution space. You can remove a lot of executions there. And then it makes the model checking process much faster. So I think similar ideas can be applied here, just in the first step, of encoding the TLA specifications in SMT, right? But I agree, it's totally crazy. When I'm thinking about it, it's insane, right? You have executions up to length 15. Why does it take a day to find the bug?
Yeah.
On the other hand, if you run the explicit state model checker, it will not find the bug. It will not terminate.
So this was done with the Apalache.
Yes, that's a new model checker.
Right, and if you use the standard model checker, it just never finishes.
You have to be very careful about how you inject faults. If you inject faults like I did, it will never finish. This I can guarantee. If you inject like 1 or 2 faults, then it might finish, but still it will enumerate a lot of possible states, right? Because here the transitions, the constraints are symbolic, right? You solve a lot of equalities, inequalities here instead of just enumerating values, right?
Cool. So, but this isn't parameterized yet.
This is not parameterized, unfortunately. What you can do, you can explore executions up to some bound, for instance, on the parameters. What we did recently, we took this termination detection algorithm by Dijkstra and said that n can be up to 10. So this is what our model checker can do. It can explore executions up to, say, 10 processes, right? So again, it solves a lot of constraints, but it's not, it's not for all n. And I mean, for a language like TLA+, it's very hard to come up with ideas for parameterized, for really parameterized solutions.
Right.
So how far we are from because you mentioned this last slide with engineers, many researchers, etc. So so how far we are from using these tools on a kind of real system like Tendermint for, let's say, n order of 100? What is your very rough guess in terms of both research and engineering, or you think that it doesn't even make sense to talk about engineering because it requires to advance the research so much that before we can really build the mature tools?
So you mean if you want to check systems of size 100, if you have 100 processes? Well, I mean, if you have very specialized inputs, if you manage to describe your algorithm in a very specialized input, you have chances, like we did with threshold automata, for instance, right? But if you take a very general language like TLA+, well, it's quite hard, right? So 100 would be hard to achieve. So
Okay.
I guess the way you should move is actually first have a very general spec, and you can check some basic properties of it by using small numbers, and then you refine it, you abstract it, right? Then you can verify, you can verify the spec for a large number of processes. So you can verify it for any number of processes. But usually people start with a very general language, right? Because it's easier to specify systems like that. Yeah. But I guess if you're trying to do, if you're trying to do model-based testing for 100 processes, I don't know what your chances are to find a bug, right? The system executions become totally non-deterministic. You have a huge system, right? So what's interesting here is that I guess you can use a model checker to produce some scenarios, some schedules that can lead to a faulty state, and try to see whether your actual system is able to reproduce this scenario. So in this sense, you do a more systematic exploration of problems in your system. Then you can try to scale to large numbers.
So this essentially is like, if I understand well, in terms of like impact on engineering, this model-based testing would be like the most obvious thing to do.
I think so, yes. But I mean, it will not be able to find you some concurrency bugs, for instance, if you have mutexes, right, and you have deadlocks somewhere. Again, you're just, it's a completely different kind of problem. So it depends on kind of problem you want to solve as well.
Okay.
Yeah.
Cool. Well, this is super interesting.
Okay.
Thanks so much, Igor, for the presentation. I think we should wrap it up now.
Yeah.
So a bunch of us have to move on, but yeah, thanks a lot. We'll be in touch online, and we'll post this shortly.
Sure. Thanks a lot for listening, and thanks for inviting me. Okay.
Thanks. Have a great day. Bye.
Okay, and you. Bye. Bye.
Next meeting.